What I want to talk about today is pulleys with mass. So typically when you have a problem, you're told, look, either the pulley has zero mass or zero moment of inertia. And if you start to add in mass, things become more complex. And when it does become more complex, it's more interesting to sort of look at those problems again from that perspective. So the goal here today is really to talk about what happens when a pulley has mass. So I'm going to do 3 examples looking at that and focus in on how that changes the problem and why you should sort of be prepared for it and how do you deal with it. We've tended to look at massless pulleys, and the reason is that these tend to be a lot easier to do. It often, when you look at these problems just generally, you have a pulley and it has sort of tension on 2 sides, and tension on both sides is equal. But when you have a mass, tension on both sides are not equal, and you can have tension A and tension B. And that's going to be sort of because of friction between the cord and the pulley, and friction along the surface of the pulley in contact with the cord drives this. So sum of moments equals Ig alpha. If the pulley is massless, I, which you can very simply sort of say is mr squared, m is 0, I is 0. If the pulley has mass, you need to apply a non-zero net moment to increase angular accelerations. And all it ends up meaning is that things are a little bit more complex when the pulley is not massless. So let's take a look at one case. And the first one is the radius of this pulley over here is given to you as 145 millimeters. The moment of inertia about its axis is Ig, which is 0.045 kilogram meter squared, and the system is released from rest. How far does the 25 kilogram mass fall in 0.6 seconds was the tension of the rope between the 25 kilogram mass and the pulley. So first of all, right away, you notice the difference, which is that I have a tension A over here and I have a tension B over here. And over there, I have an axis which I've defined x, y, and a positive coordinate system which is going to be counterclockwise. Alpha here is the direction that I expect things to move, and if that's the case, this is expected to be a negative value. Tension A is causing a counterclockwise moment, so that's going to be positive. Tension B is causing a clockwise, that's negatives, and the radius of the pulley is given. The other terms here are all acting through the center of the pulley, and so they go to 0. So because I expect it to rotate clockwise, Ig alpha is a negative value. The other side, I have tension A and MAG. So again, Newton's third law here, I've split this force, and so they have to be equal and opposite and collinear. Same thing with tension B. And so I see a positive direction. I'm expecting mass A to go up and mass B to go down. Add in those terms, sum of forces on the y direction and the A for A. I have tension A, which is acting upwards, weight, which is acting downwards, and acceleration, which is acting upwards. For B, sum of forces in y, tension B is acting upwards, weight is acting downwards, and the acceleration is also acting downwards, so that's where I get this negative. So keep an eye on what the directions are. This is not a hard problem once you draw the pictures. You can see everything and you kind of visualize. And one of the problems or challenges here is making sure that you draw the figure. So after you also have finally the kinematic relationship. Acceleration is r pulley times alpha. And you can solve through for tension A, which is 79.57 newtons, tension B, which is 92.64 newtons, alpha, which is 42.1 rads per second squared, and the acceleration, which is 6.1 meters per second squared. So if the distance traveled in this case, I know the acceleration from the previous slide, and in the time I get 1.1 meter. What would have been different if Ig was equal to 0? I have the same free body diagrams, and I can make the same argument that is Ig is equal to 0. So, the same equations, but with Ig equal to 0. All that does is it sets up the problem so that tension on both sides are equal, which is what I expected. Alpha is 45.1, slightly higher, and acceleration, again, slightly higher at 6.54 meters per second squared. The end result is that the distance traveled is going to go up, and it'll go up slightly to 1.2 meters. again using the kinematic relationships. These are problems that require you to sort of draw the free body diagram. Once you do, it becomes more straightforward to solve them. Draw the free body diagrams every time. Second one is a slightly different problem. Here I have a radius of the pulley, which is 120 millimeters, and its moment of inertia is 0.1 kilogram meter squared. The mass is given as 5 kilograms, and you have a spring constant that's given to you. The system is released from rest with the spring unstretched. At the instant when the mass has fallen 0.3 meters, determine the angular acceleration of the pulley and the tension in the rope between the mass and the pulley. So again, same diagram actually, except that I've changed TA and TB for spring constant and T over here. I have the same coordinate system with the same conventions, X and Y, and alpha, which is positive in the clock or counterclockwise direction. So this alpha is expected to be negative. M is the mass of the pulley. Now, the pulley mass again and the reaction forces X and Y at the center OX, OY are zero, are not important to the moment. And so I have Kx minus T times the radius of the pulley. Kx is causing counterclockwise moment, T is causing a clockwise moment. I have an expected rotation which is clockwise, and so Ig alpha is a negative value. So that's what I expect. On the right-hand side, I only have the tension and the weight, and it's acting downward. So I end up with the same equation as I had before. Sum of forces in the y direction equals T minus mg equals minus ma. Again, negative value. Kinematics, accelerations are pulley times alpha, and I have tension, which is equal to 43.17 newtons, acceleration alpha, which is 21.8 rads per second squared, and acceleration, which is 2.62 meters per second squared. So again, not very complex when you write out the equations, when you draw the figures. It's very hard to visualize this motion. This is a surprisingly complex motion to look at and solve without doing what I'm doing right here. If you set Ig equal to 0, all that ends up happening is that the tension goes slightly down, 37.5 newtons. The accelerations alpha and A both go up, 29.7 and 3.56 rads per second squared and meters per second squared respectively. So you now have some guidance in terms of what's happening to tension. Now, I will mention that this takes a while to solve through because the amount of equations become more and more, and each time they do, it becomes more difficult. And I solve this with a matrix inversion method when I set up all of my equations to make my life easier. Finally, this one here, which is a very complex motion. Let's not sugarcoat it. I have a mass of 9 kilograms that's attached at the bottom here, and it's attached to 2 pulleys. Both of them have a mass which is 4.3 kilograms and have a moment of inertia of 0.03 kilogram meter squared. A force of 70 newtons right here is applied. Now, what is the magnitude of the acceleration of A? And A is over here. So now we have to draw out the free body diagrams, and you can appreciate, I think, at this point, the complexity of the motion you're looking at. 2 pulleys, tensions acting on them, masses on it. But the first pulley is this: tension on the right-hand side, tension 2, which we don't know, tension T, which we do know. We know this one, it's been given to us in the beginning of the problem. We have weight acting downward, and we have a tension from the other pulley in terms of the rope connection between the two. So if you do what you're supposed to do and you put in your coordinate system, you have tension 2, tension, which are acting upwards, minus T1, which is acting downwards, minus the weight, which is acting downwards. And all of this is equal to MPAP1. So that's one pulley. The second pulley, same thing. And the only difference is that I should put T4 here. It's not on the figure. And T4 plus T1 minus T3 minus MPG equals a mass of pulley A2. So the difference between these two is the acceleration. And the tensions, of course, but that's the important thing to notice here. They're not going to be the same. Finally, the mass, which is just going to be mass G, T3 is acting upwards, mass is acting downwards, and we can subtract the two, and it's M mass times AP2, because pulley 2 and the mass are both moving with the same acceleration. We do the sum of moments about both. We have R pulley, which is causing a counterclockwise moment, and T2 R pulley, which is causing a clockwise moment. I'm expecting that alpha at the end of this is going to be counterclockwise. That's my expectation. It kind of makes sense because I'm pulling on that rope and trying to drag it upward. So it kind of makes sense that I'd expect that. Same thing with the second pulley. I have T1 R pulley to minus T4 R pulley, which equals IG alpha 2. So again, difference is this. So I have 1, 2, 3, 4, 5 equations, but 7 unknowns. So I need a couple more relationships, and I get that from my kinematics. Acceleration 1 is R pulley alpha 1. Our acceleration 2 is R pulley alpha 2. These always are problems where you have no slip. And if I solve through for it, I get T1, which is 77.1, T2, which is 61.96 newtons, T3, which is 101.59 newtons, and T4, which is equal to 73.05 newtons. On the other one, I have acceleration 1, which is 22.3 meters per second squared, acceleration 2, which is 1.5 meters per second squared, alpha 1, which is equal to 28.2 meters, or rads per second squared, excuse me, and alpha 2, which is 14.1 rads per second squared. If I had zero moment of inertia, T1 and T2 would, or sorry, T and T2 would be the same, so it's 70 newtons, and T1 and T4 are the same, which are 79.4 newtons. The only one that's different between the forces is going to be T3, which is 107.52 newtons. A1 is 4.27 meters per second squared. A2 is 2.14 meters per second squared. And again, what I expected was that I would have a larger acceleration, a larger magnitude acceleration, and I do in both of these cases. And the same thing with alpha 1 and alpha 2. I have alpha 1 of 40.6 or 40.7 rads per second squared, and alpha 2, which is 20.4 rads per second. The end result of all of this is that the complexity of these problems really does go up when dealing with pulleys with mass, because now I have a tension force that doesn't become sort of trivial. And when I do that, I have to just draw my free body diagrams. And once I draw the free body diagrams, the equations of motions are much more straightforward to do. These are not bad problems to solve because you can do it that way. However, one of the big issues that comes across, and it's not sort of communicated in this presentation, is setting up and solving for all the terms. So the last one, for example, I had 7 equations and 7 unknowns, which is a kind of a pain in the neck to keep the bookkeeping with. And I solved, and I think I mentioned this earlier, using a matrix method. So I set up a 7x7 matrix in a 7x7 or a 7x1 resultant vector, and sort of did a matrix inversion, solve through for it. Now, just keep in mind that you do have to solve for all the terms together to make it make sense. Thank you very much, and we will talk again.